class is supposed to be from 5:30 to 6.
Yeah, yeah.
6 what? 6:50 or 6?
6:45.
6:45.
Okay.
I don't want to take too. No.
Okay. Were these presentations or PowerPoints that you prepared over
Yeah,
the break?
yeah,
Or?
yeah. So I prepared like, last time I wrote this one like 2020, I think.
Oh, okay, okay.
That
Wow.
time only Jansi and I taught this class.
Okay.
This time we have 7 small yeah. I taught this one at least 3-4 times. Yeah.
Okay.
I don't have to prepare new slides.
Yeah.
GTA, it is going fine.
Yeah, I feel much better after today.
Yeah.
The 223 class went very well.
Yeah.
PLC, it was a lot more
So
people.
you are teaching 295 also, one section? No.
Just physics 223.
Okay. I think Isuran has one 295 section, right?
2 to 95 section.
Yeah, 2. So yeah, so I will send email to everybody asking for your summer preference. Already some people, especially international students, when they want to go home, right?
Yeah.
Yeah. Try to know the preferences right now, I think, earlier. We can find that.
What's what lab is taking the most in the summer? Do you know? Like it's
Summer, I think 296, 295 mostly. Yeah.
what is that? Is that
That
that you?
speed school, first semester and second semester. First semester is about mechanics and things like
Okay.
that. Second semester is electricity, magnetism.
Okay.
and things, yeah. These are the two largest.
Okay. Well,
So none of you have classes today, Tuesday, Thursday? No, this is the only class.
yes.
It's good, I think this semester most of you are taking the same classes.
Yeah.
That's a bit,
It's nice.
pump it fine here.
Yes.
Graphene one, yeah.
Whenever I left around
Now it's
noon-
close to 40 millitorr, I think.
Now?
Yeah,
Okay. That's good.
that's not bad, yeah. Okay, so let's get started. This today sound less late. So last time we talked about mostly we call the roughing vacuum pumps, right? So they can only pump to something like few millitorr. Or one thing I think sometimes you may see this, typically we call millitorr, right? That's 10 to the power minus 3. 10 to the power minus 3 is, we call the millitorr, right? So sometimes you see people call this one micron in pressure units. So 1 millitorr means 1 micron. If you say like 10 micron, that means actually 10 millitorr. So this sometimes they use that. So it's like typically when we say micron is 10 to the power minus 6, right?
Yeah.
So this is a kind of weird usage, but in pressure community they use that word. 1 micron means 1 millitorr. For us, micron is like a 1 micrometer, right? So that's 10 to the power minus 6, but for pressure they use this one.
They just love making it confusing.
What's that?
They just love making it confusing.
I know, yeah, people, yeah. For their convenience, they use these things, yeah. So up to this one, we talked about all the roughing pumps, right? These are basically, you have some rotating vane or something, they just come and trap. So this is what you are going to pump, right? So you just trap this one, in the next rotation, you just push that exhaust, just push it out, right? But here we call this something with the gas ballast, so that means you introduce little air so that they can remove this, some kind of oil or things like that. So that dry air will help to clean the contaminant in this. So this basically any lab they will have this kind of small pumps, right? Roughing pumps. But if you want real high vacuum applications, you have to use something more than these roughing pumps. So these are the things I want to talk about. First one we are going to talk about, these are high vacuum pumps. Like I said, but these pumps often need to be backed by roughing pumps. So the first one is the diffusion pump. These are pretty neat pumps, but they are not very clean. So the way it works is they have this chamber with, this is where you are going to pump on. So you have your space you want to pump. So then you connect this one, you can see the one here. So they connect your chamber to this pump. So then what we have here is actually oil, the vacuum diffusion pump oil. So then here we have a heater. So basically you with AC voltage you can heat the filament. Once you plug it in, this will heat. So that will vaporize the diffusion pump oil, right? So this oil will just transport this way. So here you have some stacks of these. So basically some kind of, you can stack these things. So these are open actually. So these kind of stacks you can put one over other. So also they have this kind of holes. So this vapor will go through here at the same time. So actually this one comes down. So from here, this vapor, because they have high kinetic energy, right? It's a high temperature. Actually, this becomes so hot, so you cannot even touch it. So that's why sometimes you have to use some running water around this one to keep it cold. Otherwise, it becomes really too hot, right? You need to. These are for this running water, the V. So whenever you have a diffusion pump, when you heat the filament, you have to start running the water. Otherwise, this becomes too hot. So then what happens is this water molecule, the oil vapor, right? So they just move here. So then it's kind of make some jets through these tiny holes. So these jets are very high energetic jets of oil particles. So that means what you have to do is what you mean by making vacuum, remove those gas molecules, right? So since these the oil jets have very high momentum, they pretty much impart that momentum to the gas molecules. So then the gas molecules will come down with because they the gas molecules will receive the momentum from those jets, right? So they just come down. So so it can be pumped out from here because they come down, right? This one. So, but important thing is, so you need to back this one. So you have to connect some kind of mechanical pump to this one. Otherwise, this alone is very difficult to operate. So whenever I talked about using any pumps system except iron pumps, I am going to talk about. So you always have to use a vacuum pump. We talk about that one, right? So this is where you are going to connect your mechanical pump. So this is your chamber. So then this has all these water molecules. Since they have this momentum transfer, they are going to come down, and they will be pumped out from this one. That's the basic principle of diffusion pump. Only problem is, so these oil vapors can backstream onto your system, right? That's not good. So that your system becomes kind of dirty. For that reason, what people do is they put some kind of liquid nitrogen buffer here. So then liquid nitrogen will condensate, so it will not get to your chamber. So otherwise, this high vapor pressure oil can get to the system. So any diffusion pump, here you have actually this is the nitrogen, liquid nitrogen buffer. So you can let you know. So it should be coming after this one. So any diffusion pump should have that nitrogen, liquid nitrogen.
Is there a reason why you use oil and not like just another hot liquid like water?
No, you need to have very high momentum particles, right? So it's very hard to get that kind of momentum also without some high viscous material. So you can see how that one works here. See, oil vapor goes through jets, right? So that's what this one. Stack transfer momentum to, that's the whole idea, right? The gas molecules, and force them down this way. So then, so you have to use the cryogenic trap. Otherwise, yeah, that's the problem is that oil backstreaming. That's why you have to put this one. So all the parts are labeled here. So the important thing is this has to be backed by the mechanical pump. I have this system in room 16 in this building. So that has the diffusion pump, and so we can easily get to like 10 to the power minus 6 minus 7 pressure. That's why we do this glass blowing and things like that. Pretty simple. You just start heating, but again you have to first rough the system, right? You cannot directly connect this one to that your chamber that is already at atmospheric pressure, right? First you need to kind of rough the vacuum. So after that you close that one and start diffusion pump. So then the mechanical pump will serve as we call the backing pump. Initially it's a roughing pump, then it becomes a vacuum pump. Vacuum is a diffusion pump. Diffusion pump does the work, but that one can handle vacuum. Yeah, you can see the water. So next one is the cryogenic pump. Cryo pump, they are kind of expensive because you need to have liquid helium. But these are liquid helium you don't have to use. It's a closed cycle liquid helium, like we have a closed cycle refrigerator. The helium gas is, actually it's not liquid helium, it's a helium gas. So then we have a compressor. So by compressing you can make the gas to liquid, right? So that's how it becomes. So you have the helium gas. So after the compressing, you get low pressure. That means it becomes cold, right? So you have this is your after going through the compressor, the gas highly compressed, then it reduces its temperature, right? So that's how it becomes refrigerant, and helium gas becomes more like liquid helium. So then this part becomes cold. So then, because this is your chamber, you need to pump, right? This one. So if you have something that is very cold, so that's we call the cold head. So this actually is connected to this one. So whenever you have a cold surface, so any gas molecule will condense onto that one, right? So that's the whole idea. So all the gas molecules will condense onto that cold surface. So that way you can remove, whole idea is to remove the gas molecules, right? That's what pumping means. So then it can condense onto this one, that way you can remove the, reduce the pressure. That's very efficient. So once you cool this one, you have to just turn on the compressor, then this getting down to about maybe close to 4 Kelvin, right? Liquid helium. So then this part becomes so cold. So then all the gas molecules in this your chamber will condense onto that surface. Then you get very low vacuum here. That's the basic idea. But the problem is, so if something happens during the operation of the system, so all the gas molecule will dissolve, right? So that's a big problem. So if you have any power outage or something, the cryo pumps will, I think, not function at all. So we have to be, that's the only disadvantage with this one. So then also at the end of the experiment, then you need to desoak that what your molecules adsorb onto. That's two words like adsorption versus desorption, right? Adsorb is something sticking onto the surface. So then at the end of the experiment, you need to desoak that one. So then you have to regenerate, and it's a little bit more work, but it's very powerful. So you can see very high pumping speed. So yeah, this momentary power loss is very detrimental. So you can have very large volumes to pump. So, but then regeneration means once you finish your pumping, so then you have to isolate. You cannot just expose this one to air, right? It's already too cold. So then you have to isolate the system, then open your vacuum. So then if you want to use again, so next time you have to make sure you remove all the gas. But most of the time when you heat it to room temperature, they can dissolve, but it's not necessarily that's true. Some molecules can be still at room temperature because it can be sticking onto the surface. So that's why you need to heat it a little bit and regenerate. So these are called the cryo pump. They are good, very efficient, but very expensive, and there are some issues with this, the power outage and things like that.
How do you deal with,
What's that?
how do you combat against power outages for using
Oh, I think that doesn't happen very often here, right? But it's in our country or something. So they have very, I think, frequent power outages, right? So it's cryo pump is out of the way. There's no way we can. But here we know, right? So it's very hardly you see any power outage. When I was a graduate student, we had a cryo pump. I remember this one happening. Then we had to wait days because when that happens, it gets exposed to air.
Yeah.
So then everything, air molecules get trapped, right? So there is a big issue. So next one is the turbomolecular pump. This is very simple thing. So this has very high speed rotating this kind of, I can show you. It has some teeth wheels. So if you look at this one, very simple thing. It's nothing. So it's something like this wheels. So they are rotating at very high speed. So then what happens is when you rotate in these gas molecules, this connected to the chamber, right? So these gas molecules will be ejected from all this because very high speed. So that's again you can get very these blades rotating at very high speed. Again transfer that momentum to gas molecules. Diffusion pump transfer momentum from those oil streams. Here momentum transfers directly from the high speed, right? So that rotational kinetic energy goes them out of the exhaust. Again, you need to have some backing systems. Always, all these systems, this is the major pump, but it has to be backed by some mechanical pump or rotary pump. So only thing is, if something, because they are always rotating at very high speed, so it can be some tear and wear, right? So that's but I have like 3 systems like this. I bought when I joined this university like almost 20 years ago. Still those are running without any problem. So it's pretty simple. It's a very small, but I have seen turbo pump this big for larger systems. Like if you look at the TEM in the Luxor, that's a huge chamber, right? They have this turbo pump, really this big one.
You have to take us on a field trip one day to show.
What's that?
You have to take us on a field trip.
Yeah,
one day
yeah.
to
So
show
I
us all
will.
this.
Yeah, I think that's one thing maybe I have to do, like show all these
Mhm.
things in the lab. Yeah.
It would really stick.
Yeah, yeah. So next one is the iron pumps. So this is interesting. This iron pumps actually you don't need a backing pump because this is so clean. So this is only thing you have is this. You have, we call the cathodes. So you have these 2 cathode plates. So then we have the anode. This anode is actually kind of you have this kind of titanium tubes. So they are arranged in kind of this hexagonal honeycomb kind of structure. These are the titanium tubes between 2. So it's more like if I take two plates like this one, this cathode and anode. So in between we have these the titanium tubes. That's all. So typically these are the cathodes. So this is the anode. So you just apply very high voltage between cathode and anode. So we are talking about like kilovolts kind of high voltage. So then what happens is now this is also connected to the chamber, right? So now if I apply very high voltage, it ionizes the gas molecules, right? It's basically high voltage breakdown ionization. Then also it's between 2 magnets. So this ion pump, these 2 are magnets. So this is basically the ion pump that has the 2 cathodes and the anode. So this is magnetic field. So when you apply this high voltage between cathode and anode, so that will ionize the gas molecules. Then you have electrons and the ions, right? So then ions will come to the positive ions will come to the cathode. So then negative ions will go to the anodes. So basically, these high energetic ions will remove this titania from the this. So actually, what are these ions? Yeah. So ions accelerate to the yeah, so these are also titanium. So titanium plates. So these ions, because this is negatively charged, right? So these are positively charged ions, they come to the cathode. So then, since they are high energy, because you have a voltage, right? So then Q times V is your potential energy. So this will give you half m V squared, very high voltage, right? These ions will kind of we call sputter, like they remove the molecules from this titanium. So then that will be deposited onto this middle cylinders. So when you remove this one with those titanium particles, all the gas molecules will also come with that, because they are also like still like a momentum transfer kind of mechanism, right? So then they will be pumped out, or no, actually they will not be pumped out. They will be deposited onto the wall of the chamber and also onto these tubes. The titanium, because in previous cases when anything comes out, they will be pumped out by the backing pump, right? So, but in this case, whatever comes out, it will come out with this this titanium atoms or molecules, right? So with that, all the air molecules come out. So they will be deposited onto the rest of the walls or onto these tubes of this center anode tubes. So that way you don't need to back it, right? So they are already deposited. That's the basic idea here. High voltage combined with the out. Then why is the magnetic field? So we know if you have a charged particle, when it comes to a magnetic field, what will happen? So if it is a perpendicular, it will go through the cyclotron one. If it is angled, it will go through helical path, right? So that means this ionized particle can move between anode and cathode in a helical path, right? So it comes here, then move back. So that way, that's how they can get more and more energies. So this high voltage causes electron to travel in a helical path with an energy sufficient to ionize the gas molecule. So those electrons have enough energy to even more ionize the other gas particle, because this is your chamber, this is connected to this is my, right? So this is my magnet. So this is the chamber that has the cathode, and center you have the anode. So they are removing the gas molecules from here, right? So then these electrons, so they are moving in this helical path. They can even ionize more atoms. So that means you have, say, whatever it can have like hydrogen or argon or nitrogen, any oxygen. So they all become ionized, right? So these ionized particles, they have very high energy. They are the ones go and remove the material from the cathode. So they will be deposited onto the rest of the walls and also onto this middle one. So that's why after certain time you have to open this one and just remove the the titanium coating from this one. You usually do the sandblasting to remove the center one. So that's typically, you can see ions are accelerated, so they strike titanium plate and become buried in the plate. So buried means what? Buried with gas molecules, right? So that's how gas molecules are going to be pumped out. So not by pumping out, by being buried in this thing. Buried gas in the plate, so no vacuum pump is required. Yeah, that's what it is. But these are big, so they are a little more expensive than turbo pumps. You can read whatever. You understand the basic idea, right? So basically you have high voltage system that will accelerate your the molecules. So then also it ionize, right? So we have electrons. Electron in the magnetic field make a helical path. So that will ionize further. So this ionized particles will sputter the titanium. Sometimes we call those titanium, they are getters. Getters means they get the molecules and bury them, right? So that's basically the getter means. You will see the word getters. Maybe you'll see the electron released from the cathode plates are constrained by the magnetic field into these helical trajectories. The potential energy of gas molecule ionized in the type is converted to kinetic energy, and the cathode sputters titanium when struck by the ion. That's what sputtering means, just removes that, right? This one. The sputtered material coats the tubes, the cathode plates, and the pump's walls. Yeah, that's basically the, you get the idea, right? Now if you look at these pumps, how they, the pumping speed, so we know pumping speed is basically that dV by dt, right? How the volume is going to be reduced as a function of time. Remember we talk about pumping speed S as dV by dt. So if you look at pumps, so typically this is very high in torr. This is 760 means 1 atmosphere, right? So now if you get to low fields, so turbo pumps, iron pumps, these ones don't work at these ones, right? Because so typically we start these pumps after we rough the vacuum, right? So up to here we don't even start these pumps. So only here, even the cryo pump. So cryo pump also we don't start until we get to this low pressure. So then you will see actually the pumping speed increases at very low pressures, right? So they work very good at very low pressure. You can see the iron pump, the pumping speed is really high at the lowest pressure, because that's true, right? Because lowest pressure means there are no air molecules, right? So that means pump can easily work at much higher speeds. But if you go to high pressure, that means you have a lot of molecules. That means your pumping speed is slower, right? So you can see. So these are mechanical pumps. Mechanical pumps, you can actually, they don't change much until you reach to kind of low pressure, right? So then after that, this speed is pretty much going down. It cannot do anything. So because after this one of these have to pick up, right? So, because if they have high speed, then you should get lower pressure. Mechanical pumps cannot work even like this is 10 to the power 3, right? That is, we call it 1 micron or 1 millitorr. So after that, they almost dead, right? Mechanical pumps, even diaphragm pumps. So they are also So after like 10, yeah, 1/10 of millitore, right? So that's doesn't work at all here. So the mechanical pumps or roughing pumps, they only work at high pressure, so they are pretty much dead here. But this like IO pumps, iron pumps, turbo pumps, diffusion pumps, they all pick up at low pressure. So it's good chart to have it. Okay, these are the basic pumps everybody should know. So now it's okay, so now we know what to use for different purposes, right? So next thing is, how do we measure this pressure? So to measure, you need to have some gauge, right? So that's what, so I'll give you some basic gauges. So for high pressures, we have this typical, we have seen this dial pressure gauges, right? It shows from like 0 to maybe whatever the number. They are called the modern, these are mechanical kind of gauges. So then little bit lower pressure, we use thermocouple gauges. I think that's something we very, yeah, even your system we have thermocouple gauges, right? So then you have the capacitance. This is very nice. The capacitance gauges, they can from high to even 10 to the power minus 3. So this very large range you can. This is very typical. So they are very good. But if you want to go to like very low pressures, you have to use this something called these iron gauges or these residual gas analyzers and things like that. So this what we use for very low pressure. Then iron gauges can be, there are two kinds of iron gauges. There's something called the cold cathode gauges, and other one is simply hot cathode iron gauges. So if you look at this high pressure, that means poor vacuum, right? They usually, you have seen this kind of thing, right? These are very standard ones, but that you can measure very, not very low vacuum. If you pump with the mechanical pump, it will show 0. That means that's all it can read, right? But this 0 means maybe not even 1 micron, right? So that's pretty. But it will tell you that it's pumping, right? So, but for certain purposes, that's enough. That's basically, you just pump from here. Then when you have some, when you evacuate this one, it kind of shrink. So then the spring actuates, and that's how the needle works, right? So these are very simple. Same thing that I from Georgia's. So by pumping the tube, you can have, this is shrinking and moving the needle. So the mechanical gauges also, sometimes they have electrical signal you can measure. To measure the pressure, you need to measure some kind of parameter, right? So most of the time it measures some kind of electrical current or voltage. So mostly it measures the current that changes with pressure. That's all you need to have, right? The pressure gauge means some parameter that has very linear relationship with the pressure. So that you can use for pressure gauge, right? Anything that has linear relationship, you can use that one. So in this one, mechanical gauges basically they apply some current. So then they have this Wheatstone bridge. So if you your system is pumping out, so maybe your resistance changes. So that can be measured by measuring this output voltage. So that's something simple. Any parameter that changes, like for example, the thermocouple gauge, or this is the mechanical, the capacitance meter. You have seen this one in many systems, right? So in this one is very simple thing. It has a kind of diaphragm here. This is a steady electrode. They have this diaphragm. When you pump the system, this diaphragm will move, right? It becomes initially at room atmosphere pressure. Suppose it is like this. When you pump, it might kind of curve, right? So when this happens, what happens? The capacitance between these two plates become different, right? So they can directly measure the capacitance. That capacitance is directly proportional to the pressure. So that's how this capacitance will give you the pressure value. That's very simple. So here, from these are two electrodes, you have to measure the capacitance by measuring the voltage across this one. So yeah, that's it. So with the pressure, your capacitance changes, that will give you the pressure. So thermocouple gauge. This is the most common for, you can get down to like reasonable low pressure. So even like 10 to the power minus 4 kind of pressure you can easily measure from thermocouple gauges. This is a very simple thing. Actually, thermocouple gauges, what you have is, so basically you measure the temperature, that's all. So this is what the thermocouple gauge is. You have a filament here. So this one is the filament. So that is in touch with this it can be the thermocouple to measure the temperature, right? So now, so this is connected to your system, right? So now what we do is, first you pass a current and heat the filament. So that's basically, if you have this filament, if I pass a current, what happens, you just heat this one, right? So then I have a thermocouple too. If it is in contact, I can measure the temperature from the thermocouple. So that's all we have to do. Because now, just imagine if you see, because this is connected to your system, right? This is where the pressure is going to be measured. So if it has a lot of air molecules, what happens? When you heat this one, that heat will be transferred to those gas molecules. So if you have a lot of gas molecules, a lot of heat will be transferred to gas molecule. That means this temperature will be less, right? So then if I pump this one, you have less gas molecules, then the temperature will be not that low, right? Because you don't give that much heat. So now if you completely pump, you have only few molecules, then the temperature will be even higher. So by measuring this temperature, you can directly get the pressure. That's basically what they do. So if you read this one, very simple technique, right? It's just basically, you can see filament is heated by some current. So then filament is exposed to the gas, right? So that's where the measure. The heat in the filament is transported to the gas. As the pressure decreases, the temperature increases, right? Because less heat is given. We measure the temperature of the filament by a thermocouple. That's all you have to do. Right? Then you have to have some little electronics, right? Do some AD converter or something. So that's pretty much all it. So these are the thermocouple gauges. But there's something called the Piranha gauges. In that one, instead of a filament, they have a just simple metal. Same thing, right? You don't have to have filament. If you have metal, then still you can heat it, right? So that way. So that's why. So some resistor. So instead of. So here, typically, thermocouple gauge use a really wound the filament. So in the Piranha gauge, basically they use a simple resistor. It's the same thing, right? You heat this one, so then you have the thermocouple measuring that temperature. Very simple technique. Here, this is how the, so I think everybody should have seen. This is how the thermocouple gauge looks like. But now you have this digital ones. So Piranha gauge same as this one, except you have resistor instead of the filament. So So then the hot cathode gauge. So how does this work? Again, you have, because this is where this is connected to the vacuum system. So you have a lot of molecules here, right? In the hot cathode gauge, you heat your cathode by passing current. So basically you have filament here. So by passing a current, you can heat the filament, right? So that's what this is doing. So then by heating, then you can, so this has air molecules. So by heating, you can emit electrons, right? It's called the thermionic emission. So these electrons can collide with these air molecules and give that energy. And also by applying very large voltage here between the anode and cathode here, so you can actually no. Here we are applying large voltage. Here is a grid voltage. So this is where you are measuring the current between these two. Suppose if I have a lot of gas molecules, what happens? So these ions, so they will have a large current, right? So if you pump the system, then you have less number of ionized charges, then what will happen to this current? That will be less, right? Because if you have more, then you have larger current. If you have less number of ionized charges, you have less current. So that means directly that current is proportional to that vacuum. That's basically how the ion gauge working. So this with these two basically attract these electrons more efficiently. That's a very simple thing, right? So you just thermionically emit electrons that will ionize the charges. So then you just measure the ion gauge. You don't have to apply really high vacuum, the voltage. So you only have to apply enough voltage to guide the electron. Is that it? So just by heating, this is called the thermionic emission, right? So everybody remember, what are the ways of emitting electrons from a surface?
Photon.
Yeah, one is a photo emission. Yeah. Other one is thermionic. Yeah, if you heat above the work function, you can emit electrons. Other one is the field emission. If we apply really high voltage, right, so you can emit electrons. That's what the field emission means. That's why all TVs we had this cathode ray tube like big. That's basically like 10 kilovolts kind of voltage. These are the typical three ways of emitting electrons. Right? So here we are talking about thermionic emission. By heating this one, you emit electrons, so they will ionize the charges. So then these charges will be attracted to anode and cathode. So you can just measure current. So the current depends on the vacuum, right? So if you have less number of particles, you don't have, if it is really clean, the current goes really low, right? Because there's no charges to pass through here. That's the basic mechanism of, this is the hot cathode gauge. So then there's something called the cold cathode gauge. In this one, no filament or anything. So you just apply, it's more like a field emission. You apply very large voltage between cathode and the anode. Yeah, so then you emit electrons by, it's more like a field emission, right? Due to the voltage. So then you have a magnetic field. So the magnetic field will make those helical paths, right? So that's how they move, and the process you can measure the current. That also depends on the pressure, right? So we just basically read the current from anode to so we have to measure this one. Yeah. So because we are applying voltage between anode and cathode, you just measure the current from that one by applying have something. So even if you apply very large voltage, you don't get current unless there's a path from here to here, right? So that path comes from how if this is connected to some pumping system or something. But by removing these molecules, you can see how this current changes. That's all. Right? That's what this is about here. Between this anode and cathode, we just put a ammeter like that. So then you can measure current from that one. So, I think everybody familiar with how, if you have a electric field, you make this electron very high speed, right? So then when it enters the magnetic field, you know, if it is perpendicular, it goes through the cyclotron orbit. If there's any angle, it goes through the helical, right? That's how this van, what is the van? This, you see the Van Allen belts, right? So you see from the north and south pole. So exactly same thing, right? So you see this happening here. That's why when this happens, due to the acceleration, it emits radiation, right? So the aurora, because there's some ionization, then you have these charged particles, right? So then we know the magnetic field at the poles, because of that magnetic poles, they starting to go through this helical paths. That's acceleration, right? So when any object, charged object accelerates, what happens? They emit radiation, right? So that's basically, so it's the same mechanism here actually. You ionize, and then you have enough energy. At the same time, you apply magnetic field to make that helical path. So, yeah, this ion gauge that we talked about. So, the ion gauge is basically hot cathode gauge, right? That's the difference. Okay, so these are, so you have this one is basically to emit the heat, this one, and emit the electrons, right? So then you just measure the current. So depending on the current you use, whether these ions can reach here, you will measure this current. Basically, this is a hot cathode. The ion gauge is basically hot cathode gauge. I have all these things in my lab, all the systems we use. If you want to measure anything like 10 to the power minus 6 or something, you have used the ion gauges. I have used all these, cold cathode, hot cathode, and everything. So leaks, so any vacuum system, most annoying thing is leaks, right? Whatever you do, you have to be really careful. So you can always have leaks. So mostly they can come from O-rings. So because you can never make good contact with metal and metal, right? So typically we have to put kind of rubber O-ring, so that can make the good seal. So O-rings, so, or it can be a metal gasket. So sometimes we use copper. So okay, copper, if you press, they kind of become soft, right? So that can make a good contact. But if you just put two surfaces like this, even if you apply very high pressure, you can never make a good seal here, right? Because if you look, this surface is pretty much, it's not flat, right? So then what do? Basically you make a O-ring connection here. So basically you have to kind of O-ring groove, so that O-ring is sticking out like that. From the other end also, you have that kind of O-ring groove. So then when you press these two, these O-rings can make the contacts. So you don't need to have two, you can have just one O-ring making the both connections. So it can be rubber O-ring, or you can have a copper gas cut. So copper also, when you press, that become kind of, so copper gas cut you only can use once. So after that you have to just throw away because it's already crushed, right? But if you use white on or Buna, those kind of O-rings you can keep using. So yeah, metal gas cuts. Then if you use some electrical feed throughs, if you have a vacuum system, so if I want to put some, we have to make sure good seal here, right? So that those are the places you can leak. Shut off valves. So if you have some pipes, they can leak from where you, if you have two tubes, right? Typically we are going to solder or weld, right? So those things also, if you don't do properly, they can leak from those things. So yeah, welding. And so if you have a vacuum system, you have to be really careful how to make a really good vacuum. It's very annoying sometimes. You cannot find where the leak is, right? If you have 50 connections, so we know the system is leaking, we don't know exactly where the this one, yeah. These are some of the reasons for poor vacuum. So sometimes if you have pump oil contamination or so if your pump is not working, so outgassing is a very big thing. Like if you have a lot of gas molecules attached to your chamber wall, so they don't come out easily, right? So then when you start pumping, they start to come out. So that means at very low vacuum, if you have a gauge, you will see the pressure keep going up because those outgas, the outgassing of those molecules, that can make the vacuum bad. Yeah. So helium kind of thing is very difficult if it is get trapped in these things. Yeah. So the leak detection. So if you have a big leak, that's very easy. So what we typically do is, if you have some, suppose this has many connections and I just draw something like this. You have some connections. So then if I, yeah, this one. So one way to do is first close everything, then you can pressurize this one with some, suppose if I have a tube here, I can enter maybe helium gas or nitrogen gas. You can pump it and just put some soap solution around all these connections. If it's a big leak, you will see some bubble coming out, right? So then you can see there's a leak. But that you can only do is a real big leak. If it is a tiny leak, so you cannot get to the lowest pressure, but it's very difficult to see where the leak is. So in that case, you have to use something called this leak detector using a mass spectrometer, like helium mass spectrometer. What we do is, you just pump the system. So then I connect this one to my pump, and I just pump the system. So then we have to, so then this is also connected to some, yeah, so let me do this one. If I have this one connected to this mass spectrometer, this is a pump, this is a mass spectrometer. So after I pump the system, so even while pumping, I can spray helium. So suppose this joint, right? If there's any leak, so helium will creep through here, so that will be detected by the mass spectrometer. Actually, this mass spectrometers, they are kind of, it has a audible sound. If there's a leak, that will give a very annoying noise. So, but that way you can say where the leak is. Basically, that is the everybody remember the mass spectrometer, right? Basically, you have this high energetic ions coming out, then you have magnetic field to curve it, right? So that depends on the mass. Okay, so remember, if you have half mv squared is the voltage times your potential energy. This is the voltage you apply between the this electric field. Then when it comes to the magnetic field, it goes through some kind of cyclotron orbit. So then we know mv squared over r equals the force is qv cross b, right? Lorentz force. From here you can find the radius of this one that depends on the actually mass. So you have done this problem, right? So you can see depending on the mass, it goes through different parts here, right? So basically, but in this case, we only care about helium. So helium comes to your detector, right? So then, if you have any leak, you just directly observe from this one. So, but we have to be very careful. So when I hold my, what we do is here, I have helium cylinder here, right? I just pump it. So then I just use my nozzle and just spray on this one. So what happens if I start from the bottom? So when you, suppose I spray here, so then I hear some noise, then you think this is coming from here, right? But you have to be careful because helium is a light gas, so it can easily move here, maybe leak is here. So it may be that sound is coming from here. So if you use the helium detector, you never start from here. You start from top to bottom. So you just go through here, make sure nothing is leaking, then you come down. So you never start from the bottom. If you start from the bottom, you will hear the leak sound, but it's not where you are aiming at, right? It may be coming from here. So one thing, remember that one. You never start from the bottom. Start always from the top and gradually come down. Leak detection needs lot of patience. So it's, you cannot immediately. So you will definitely hear the sound, but to find exactly where, you have to do very smart way. So otherwise it's very hard to find where the leak is. So then you have to isolate some parts, right? You just and see different parts and things like that. Then you get the idea, right? So leak detection, this is very important.
I'm trying to
Yeah.
picture this from the vacuum pump in the container. So whenever you say starting from the top, do you mean like furthest away from the vacuum pump?
No, I'm talking about if you have this
Or you're talking about the
connections,
vertical
yeah. So like suppose these are the possible leak places, right? So then you start, this is very simple one, but it can be complicated one.
Yeah.
So always check any possible place from the top, then the next one like that, then gradually come down like that. So if you do hear, you hear the noise, but it's not be from here. It can be somewhere from the other part, right? That requires a lot of patience. So this leak detector can be. I have one next to your system. We have that big thing. That's the helium detector. But only thing you need is a helium gas cylinder. You need. Right? The one thing I was proposing to you to use that one to check any obvious leak in your system, right? So maybe something you should do just to get some experience. You have seen that one big box sitting next to that one?
I might have seen it, but I'm not conscious of what it is.
There's a cart, right?
Okay.
Yeah.
Yeah.
The cart, there's a big instrument.
Yeah.
That's the helium detector.
Oh, okay.
Yeah. So sometimes people use this RGOs, something called this quadrant called mass spectrometers and different things. That's essentially same thing. Okay, so I'm going to stop here. So then I will quickly, is there any question from here? So these are some basic things, right? So you might not get everything today, but one day when you see these things, you might remember, okay, we have discussed about this someday. So I want to discuss something related to this one. So it's, I think that's the best to do this one. So yeah. So related topic is film deposition. There are many film deposition techniques, right? So I think I thought this is a good place to discuss a little bit about this one. So you all have done some deposition, right? Metal deposition, or but there are so many different things like atomic layer deposition, CVD, and all these things. So that's what I want to quickly go through this one. So basically, film deposition is what? You just take some material from one source and just deposit on the substrate, right? That basically the deposition means. So, but when you do this one on the surface, so you don't get this is deposition like one after other, right? What happens is maybe it gets started here, then it has to diffuse through this surface, right? So this is actually it's a diffusion process here. So it has some kind of activation energy here. So on the surface it diffuses according to, so everyone remember this kind of equation? What is this equation? It's a Arrhenius kind of, that's a called the activation process, right? So anything, so that if you have to go from one state to higher state, it has to overcome this kind of barrier, right? So if you have to go from here to here, we call this a barrier. So if you have that kind of thing, it always follows this kind of some property. Suppose it can be A equals A0, E minus E over KBT. So that means you need to overcome, this is this barrier energy. So this is called the Arrhenius kind of, so this is called the activation process. Activation means you need to overcome some barrier. So even semiconductors, we have this band gap, right? So that's band gap you have to overcome if you want to promote electron from valence band to conduction band. That's a Arrhenius process. Diffusion also that kind of process. If you have atom here, if that atom, if it has to diffuse, it has to overcome some kind of this barrier. So, but if you have to have a good deposition, so you need to have enough diffusion and to selectively choose where it wants to sit, right? That's the important thing. So that means you need to either use right energy to give this one, or sometimes you have to heat this surface to give the right conditions for these atoms to be deposited. So that's why you need to make sure that has right energy. So this, maybe that energy you can get from like some applying voltage or heating that entire system. Also how it deposits on the other substrate also, right? So typically when you do these films, so people mostly use the evaporation. So evaporation means you have, remember we talk about this nice vacuum system. So vacuum system means if it is a very high vacuum, it's in the molecular regime, right? It's not the viscous regime. So in that regime, your mean free path is very long. So that means it's very easy to deposit. So suppose if I had this chamber. Remember, we had this chamber, then we had, suppose, so then we put the pump for the mechanical pump. This is basically, this is my mechanical pump. So then I have a gate valve here. So this can be diffusion pump or cryo pump or what is that, turbo pump, but for iron pump, but if you use iron pump, you don't really need any vacuum, right? So then we use this one. This is basically the system, right? See, how do you do this one? First, you just open this one and you close this one. So then you pump this one to some, this is a mechanical pump. So then you rough this one. So after that, what we do? We close this one and open this one. Now you are exposed to this one. So then we can open this one to vacuum, right? That's all. So this is the entire system. So now if you do this one, you can get this one to molecular flow regime. So in that case, I can have some material I can heat, suppose if it is on something. Suppose tungsten, if you heat to like 2000 Celsius, I can evaporate this one. But these molecules, so you have very long mean free path, right? So that means I can have my substrate here. So this one will go here and be deposited onto this one. So that's simple system, right? So this one I can heat with maybe by passing a current. So typically you have a boat or you can have a spiral coil. So this is a basic deposition system. So here you can have your substrate and then molecules. See, if it is not high vacuum, what will happen? The atoms of molecule, they will not reach here, right? Because we have other gas molecule, they will interrupt you. So that's why we have to make sure high enough vacuum, so that will help you get there. So that is basically evaporation. This is nothing but evaporation. So then the very fancy evaporation technique called the MBE is a molecular beam epitaxy. So that is very expensive system. But this is you can make for very like few $100 you can make this system.
Do you have to have high temperatures for the absorption?
No, so actually for absorption it's good if you can cool this one.
Okay.
If you cool, then these molecules will absorb much easier.
Why is that?
So because of low temperature, so absorption coefficient is higher, right? So the impinging, so we call the impingement, so that will be higher if at lower temperature, rather than happening this one. So once it hits, it will stick. So you have higher impingement. So remember 1/4 of that V bar times P something. Yeah. So yeah, then we have chemical vapor deposition. So like you are doing, what we do is you just we have gas species, we just dissociate the gas. So then those gas molecules will be deposited onto a substrate. So like in your case, what are you doing? You have methane gas, you decompose methane into carbon and hydrogen, then carbon will be deposited, right? They can make a nice film like that. So that's a chemical vapor deposition. You need to have a gas and substrate. So next one is the sputtering system. Sputtering means you have this high energetic ions. So the ions will remove molecules from the target, so that will be deposited on the substrate. So there are many sputtering systems. You can have regular sputtering, then you can have the reactive sputtering, and there's a So but this can be a little more expensive. So these two are very simple. This is the easiest, right? You need to have simple quartz tube and the furnace and gas flow. These two are very simple. This is the most expensive molecular beam epitaxy. I don't think anybody around here has a MB system. So I think I know Notre Dame has some, so those places, maybe Purdue has very few places they can afford MBE system. But this is also not very difficult, so, but you can have simple the DC sputtering. So the sputtering can be anything, right? So then our evaporation can have, yeah. So this is also important thing. So like low energy deposition, if we have low energy, that means they don't have enough energy to overcome that diffusion barrier. So that means they don't diffuse, instead they just make islands. Because to diffusion you have that barrier, right? Diffusion barrier. So if you don't have enough energy, they won't diffuse here. That's why you have, if you deposit, you get kind of islands kind of. But if you have high energy, even sputtering and things like that, it can overcome that diffusion barrier, so they can make very nice deposition. But if you want to yeah, so but MBE, what they do is you need to find the exact right substrate. So if you have that substrate, that reduces the that diffusion barrier, so that way you can make better things. But for high energy deposition, you have enough energy. So only problem is you can have this intermixing. If you have sometimes maybe two different molecules, they can intermix with that one. That's the only disadvantage. So here, this is what I was trying to explain, right? So here, you make this high vacuum system. This whole thing is this one. So here is the source material. You can keep this one. So then this is where you keep your wafers. So it's good if you have it in this spherical one, because we know it's spherical symmetry, right? So you can, rather than if you put on a flat surface, you don't get exact same flux, right? But if it is in a spherical symmetry, you get the exact same flux, you get very homogeneous growth here. So this one can be, sometimes we use some kind of board, so tungsten board, then we put the material. Suppose if I want to deposit copper, you just put it in this tungsten board, then tungsten board can be heated by passing a current. Right? So basically I squared R current. So, but you have to be careful when you heat this one. How do you, suppose I have to apply like 100 volts, but also I want to get very high current, right? So I square. So how do I get that one? Because this is a metal. Tungsten is a metal. So I have seen people trying to use a variac, like 120 variac. You just increase, then you blow the fuse. Because you cannot, because this is a metal, right? You cannot have too much current passing. So what you have to use a step-down transformer. So if you use a step-down transformer, then you can increase the current, right? So that's what I think any sputtering system, like you can come in the room 25 we have, there are a lot of step-down transformers. So then you can have a higher current, because we know V1 I1 equals V2 I2, right? So if you want to get this one high, so with low current, then we have to have this one low, right? So that means first you have to bring the voltage down with a step-down transformer, then apply the current. Just try connect to this one, so you will immediately blow your fuse, right? Because this is a short almost. Or you can use this kind of spiral one. Then you have to hang this, if I use a copper, you have to get copper kind of what you call it, strips kind of thing, and they just attach to this one. then if you pass a current, still they can operate, right? So like that. It's almost time. Yeah. So that is also, this is called a simple vacuum deposition, but if you go to the clean room, they have something called the E-beam evaporator. Rather than using thermal, they use the electron beam. They have this filament, thermically heated filament, so that they have very high energy electron. That electron will melt this material. Rather than melting by heating this one, you use high energetic electron beam to heat this one, but same mechanism, right? So still you will, this is the loop I was talking about. So this is also a little bit expensive. Clean room has the E-beam evaporator. We have the thermal evaporator. Actually, if you go to Dr. Sergio Mendes' lab, he has a sputtering system. So he can deposit different.
Over in the Shoemaker building?
Yeah. He has a sputtering system. Then we have a lot of these CVD systems, right? So, okay, so I will stop here. So read this one. So next, I will quickly go to the sputtering system. Sputtering, there are like DC sputtering, RF sputtering. So basically, you have some material, target material. This is the target. Yeah. If I want to deposit, say, copper, you just get this one, and this is where my substrate is. So then just basically apply very large DC voltage. So then what happens, you need to have some inert gas, argon gas. So then what happens, this argon becomes ionized. So we make a kind of, we call a plasma here. Actually you can see nice color here. So in this one, so these argon atoms, they will sputter system, they will deposit onto this one. So, but this you can only use for metals, right? Suppose if I want to deposit some insulator, I cannot apply DC thing, right? So then we have to think about some radio frequency sputtering system. We'll talk about that one in the next class. Maybe 15 minutes I can finish this chapter. Yeah. This is all about different film deposition. Okay, I will stop here. Maybe at the end of the class I will take you for a tour, then you will get a better idea, right, what I'm talking about. So CVD, and even we have a nice something called this, Consent has MOCVD, metal organic chemical vapor deposition system. Yeah. Okay, yeah. So I'll see you Thursday, right? Then we finish this chapter.